Thank you, Brian. My name is Sven-Arne Reinemo from Simula Research in Norway. The topic of my talk today is closely related to this morning's keynote by Professor Duato. It's related to congestion control, and he presents a very simple but practical approach to improve performance in the case of congestion. It's not the final solution to congestion control, but it represents a way to utilize both old and new InfiniBand equipment. So before I go ahead, a few acknowledgements to some colleagues at Simula that has all contributed to this topic. They deserve their thanks for their contributions. So quickly, let me go through the agenda. First, I will go through the motivation for, or the reasons behind network congestion, why it happens, and how it affects throughput negatively. It will be in part a repetition of what we did this morning, what Professor Duato did this morning. Then I will talk a bit about virtual lanes and how this can help us to avoid or to reduce congestion. Then I will briefly present the proposed vFtree routing algorithm that we have prototyped in OpenSM, followed by some experimental results and some simulation results testing this prototype. So, what is congestion? This is something that happens in the network because we have a lot of shared resources, and when we have hot receivers in the network, these resources are overloaded, and in lossless interconnect such as InfiniBand, this will lead to something called head-of-line blocking. And head-of-line blocking is the core problem that we need to solve, because this reduces the performance of flows not accessing the hot receivers. So basically they are considered innocent flows when congestion occurs, and we commonly call them victim flows. There are ways to reduce or remove congestion, such as InfiniBand congestion control, which we discussed here last year. We have also published a paper on this in last year's IPDPS, which is available for those of you who are interested in InfiniBand congestion control. But I won't talk any more about this today. So let's have a look at a simple test scenario that we put up in our lab. We have 8 hosts connected with 2 switches, and in this scenario we have, is this working? Yeah. We have the switch-to-switch link, which is a QDR link, while all the host-to-switch links are DDR links. This is just to emphasize that bandwidth is not a problem. So this is not a problem that we can solve by adding more bandwidth in the network. It's basically what happens in the switch and the head-of-line blocking that causes the performance degradation that we will see a bit later. So let's add a few flows to this scenario. We add 3 flows towards host 6, which becomes the hot receiver, and then host 2, 7, and 8 are contributors to congestion towards this host. Now, this is not a problem in itself, because right now the link towards host 6 is saturated. And we are utilizing this link at its full speed, but since we are using lossless flow control, there is back pressure in the network, and that means that buffers will fill up all the way from the destination back to all the sources. So first they will fill up in switch 2, and that will further back pressure towards switch 1 and to all the sources. And then we have a congestion tree created in the network. This congestion tree is present because we are adding trying to send more traffic towards host 6 than it can has the capacity to receive. So this is just a well-utilized network. The problem happens if we add a victim flow, which in this case is from host 1 towards host 5. Now remember that this link is a QDR link. That means that it is the path from 1 to 5 should be able to send at full DDR capacity of host 5. But due to the head-of-line blocking, this will not happen. Because now the flow from 1 to 5 will still be will be a victim of the same congestion tree as the other flows. So it will receive back pressure from switch S1. And this is because the way the packets are organized in switch S1, the packets headed toward the congested flow in congested node host 6 is blocking the packet towards host 5, basically rate limiting the throughput of the victim flow. So if we try this setup in the lab, let's look at the results that we will receive. Remember that flow 1 to 5 is the victim flow, and the other flows are all congested flows. So the results will look like this. For the congested flow, there are 3 flows sharing a single DDR link, and they get 1/3 of that link each, which is fine. That's the best we can hope for in this scenario. But we also see that the victim flow from 1 to 5 is limited to the same performance. And this is again because it is a head-of-line block by the congested flow. So this shows the severity of the situation, because ideally flow 1 to 5 should achieve about 13 gigabits of throughput in this scenario. So how can we fix this using virtual lanes? Well, if we look at what virtual lanes basically are, it is a set of it is a logical link that shares the same physical resource, but they have independent buffering and flow control resources. And the most obvious and most common usage of virtual lanes are quality of service, which some of you might already be utilizing virtual lanes for. Basically, we can classify a set of traffic into different classes and then map these classes to different virtual lanes in order to prioritize traffic. Okay. So that's one use of virtual lanes. We will use it a bit differently to improve performance and avoid or reduce the negative effect of head-of-line blocking. If you have a quick look inside a conceptual switch, we see in this case that we have for each physical link we have 2 virtual lanes. Now let's manually map the victim flow to one queue, and then we can map the 3 hotspots flows to a different queue. And then we don't have any head-of-line blocking anymore because they have a separate set of resources. And if we return to our results, and this time adds the results for the 2 virtual lane case, we see that there is no longer any negative effect of the head-of-line blocking because this flow is no longer head-of-line blocked. So this serves to show the gain that is possible by using virtual lanes to avoid congestion. Of course, in this scenario, we did a manual mapping. We knew exactly how the flows was assigned, etc. So this is not practical for your applications, but it shows the gain. And we will use this fact to improve performance with vFtree routing. Now, virtual lanes might be used for quality of service, but based on our experience, it might be different. But in our experience, virtual lanes are rather seldom used. They are mostly left idle, and only one virtual lane is used. Sometimes a few are used for quality of service. if the routing algorithm was able to utilize these virtual lanes to improve performance, then it would be possible to avoid many cases of head-of-line blocking. And that's basically what we are doing. vFtree routing is an enhancement of the existing factory routing in OpenSM, where all source destination pairs are mapped statically in advance to various virtual lanes. And this is distributed depending on the number of virtual lanes allocated to the algorithm, and trying to distribute traffic as evenly as possibly between the available virtual lanes. So this is not, it does not consider the traffic dynamically, but it does a distribution beforehand. So there is less statistical chance that you will reduce congestion. But of course, certain cases will still be congested because there is not enough virtual lanes to handle all combination of flows you could have in your network. But the bottom line is that it would never give worse performance, but in very many cases it would give better performance. So let's look at these results, and the more details about this algorithm is presented at this year's IPDPS Pro conference in Alaska. And if you're interested, you can also have a copy of that paper by just contacting me. Now let's look at a slightly more lab setup. We have a small factory consisting of 4 switches and 6 hosts. In this scenario, host 1, 3, and 6 are sending to host 5. So host 5 is the hot receiver. And additionally, we have 2 victim flows, from 2 to 3 and from host 4 to 1. And in this configuration, these flows are the victims of head-of-line blocking. For flow 2 to 3, this happens in switch A, so we see the similar scenario as we saw in the simpler example. But this time, since the flow from 2 to 3 and 1 to 5 are sharing the same upwards link in the factory, flow 2 is head-of-line blocked by flow 1, since this flow is accessing the hot receiver. So it means that it's reduced to 1/3 of possible bandwidth. And we see the exact same for switch B, where the switch from 4 to 1 is blocked by the flow from 3 to 5. So if we look at some result, this time we show the total network throughput for 3 different combinations. If you choose just one virtual lane, which is the default scenario, we would see approximately 20 gigabits of throughput. If we spread traffic across 2 virtual lanes, this increases to about 27 gigabits. And adding a third virtual lane, it increases further to approximately 29 gigabits. So we see that by adding virtual lanes, we get an increase in throughput. But we see here that the most benefits are achieved when going from 1 to 2 virtual lanes. And this is basically because we are lucky and we are placing some of the flows on separate virtual lanes so that the victims no longer are affected by the congested flows. If we look in more detail at the individual flows, then we will see several interesting cases. Remember that the 2 first flows are the victim flows, while the 3 lower ones are the hotspot flows. So with using only one virtual lane, we see that the victim flows are reduced to the same performance as the congested flows, except for flow 6 to 5. And flow 6-5 sees higher performance because it's closer to the hot receiver. This is something called the parking lot problem, and occurs because the distance is different between the switches, and then it's arbitrated to receive more a larger share of the last link towards the hot receiver. So this is separate from the congestion issue and the head of line blocking, but it makes its appearance. If we add a second virtual lane, we now see that the flow for the victim flows, the throughput for the victim flows is increased. It's approximately doubled. For the congested flows, the throughput is still the same. If we add the third virtual lane, we can see a slight improvement for the victim flows, and we also see that now the throughput between the congested flows are fair. They each get the equal share of their bandwidth. And this happens here by coincidence because we have 3 virtual lanes, and these 3 congested flows happens to be distributed to each of their virtual lane. And that means that we get a fair arbitration at the last step, and they avoid the parking lot problem. So there are several benefits from using virtual lanes in this way. But again, it's not predictable because all the distribution of virtual lanes are done in advance. So if we now look at some HPCC benchmarks run on the same scenario where we replace the victim flows with a few processes running the HPCC benchmark, we can see that this performance is increased by approximately, or latency for the random ring is reduced by 34%, and the random ring bandwidth is increased by 32%. So there is decent performance increase for this very simple optimization. Of course, for the final application measurements, things would be different and depending very much on the communication pattern. If we look at a slightly larger scenario, we have simulated a 648 port 2-stage vFtree, which is the largest vFtree, 2-stage vFtree that we can build using 36 port switches. And this is something that several vendors these days provide. And on this topology, we have applied a traffic pattern that consists of each host sending 5% of the traffic to a hotspot, and the 95% remaining traffic to uniform distributions. So this is not a very realistic traffic pattern, but it catches the fact that usually there are a few destinations that see a lot of traffic, which is a common phenomenon. So let's look at this scenario with an increasing number of hotspots as well as an increasing number of virtual lanes. With one virtual lane, we see slightly less than 2 gigabits for one hotspot. It increases a bit for 3 hotspots, and it's almost 4 gigabits for 9 hotspots. So why does it increase when the number of hotspots increases? That's because the groups that sends to a given hotspot, in the first case, all hosts are sending to the same hotspot. In the second case, there are 3 groups of hosts that is sending to 3 different hotspots. So each of them get a higher share of the bandwidth towards the hotspot. And this is further reduced for 9 hotspots. So this is perfectly as expected. Adding 2 virtual lanes, we see a huge increase in performance again. And this happens for all scenarios, as we are able, again, to avoid some of the head of line blocking and thereby increasing performance. 3 virtual lanes, we see further increasement, but we see that, again, the largest amount of improvement is found when going from 1 to 2 virtual lanes. And there is some incremental improvements when we add further virtual lanes. If we go to 6, there is still some improvement, but it's even less. And at 8, it's just a very small improvement. But by now, we're able to fully utilize many of the links in the network are we ending up with an average node throughput at around 13 gigabits per second, which is what is the ideal rate for this configuration. So the main thing to take away from this is that by going from 1 to 2 virtual lanes, we see a huge increase in performance. We will still gain more performance by adding more flows, but if you would adding more virtual lanes, but as long as you only have two virtual lanes to spare for vFactory routing, you can see huge gains. So that makes it possible to combine this with, for instance, a few level of quality of service as well. So that's a conclusion. We have implemented this algorithm in OpenSM as a prototype and tested it in the lab as shown here. And we have run a lot of different traffic patterns on this setup, both in simulations and in the lab. And we generally see from this that we have from 38% to 757% increase in throughput. And we didn't have any cases where we didn't see any increase in throughput, but we know that if we wanted, we could make such a configuration by placing the flows in a way that no improvement will be possible. So again, it's not perfect, but it's something that can be applied to any type of InfiniBand network, old or new equipment. It doesn't rely on any specific features in hardware except for virtual lanes, which is common in all InfiniBand equipment. We also will look further into this to study how we can improve further by making a dynamic allocation of virtual lanes during runtime based on the placement of new flows in the network, which could probably further optimize the results. So that concludes my talk.